Hey, let's start. Taylor is going to give you your test back. So the the scores are posted in MyMathLab. So I already sent an email message about that earlier, but if you didn't see that, they're there. So you're in MyMathLab, I think it's called overall score or something. Well, I don't know what it's called, okay? Anyway, your total grade, which you can find there, your current total grade there in MyMathLab. So that's pretty up to date, okay, as of today, because the test is in there, right? So for many of you, your current score, your current class score went up, all right? The test helped you. For many of you, all right? So that's good. For some of you now, you're over that magic 70 threshold, which is really important to get a C, and then others are really close. So we've got this third test coming up, right? Soon, November the 25th, because of the quirk of the calendar this year. The last class day before the final is November 25th, so that's when the test will be, right? The last test. So we're really on a short time frame here, and then the final is after that. But I forgot what day the final exam is. Okay, and then plus whatever homeworks we're doing, right? So those are your opportunities to get your score up. Above, whatever to whatever grade you want, right? That you're looking forward to or that you were hoping for in the class. Okay. The final counts a lot, though, so that's still really a big opportunity to improve your score in addition to the third test. The remaining homework is important to prepare for those. I don't know how much you can improve your homework score now. We've got so many homeworks already out of the way, right, that an individual homework assignment may not change your grade that much, but test number 3 really will, and then the final exam will also, okay? Now the answers are posted, so I posted the answers on those are posted on the Blackboard page, right? Same place the test number 1 answers were posted. So as usual, right, you want to take the opportunity to correct your mistakes, okay? Not just look at your mistakes, but actually try to correct those. So you may try doing that in the Math Center. So not many of you have been visiting the Math Center, okay? Because I get reports on that, but time to think about that, especially if you are still underwater, right, on your grade, okay? Still have a chance to make that up, but we're running out of opportunities here, and also just days in the course, right? So here's the current homework list. We finished with Chapter 2. We're talking about parabolas, or quadratic functions, right now. So that homework, that first 3.1 section was due tonight, but I moved that back a little bit. We're still talking about things from that section and also from this section 3.2 as well. Okay, so all these homeworks pertain to parabolas or quadratic functions. And we're going to do today, after the lecture, we're going to do an activity sheet. I don't know if we'll get through it all today because it's got 3 kind of, well, they can be difficult problems, all right, to do. It's definitely something that working with your group will help you with. But anyway, we'll try to get as much of that out of the way as we can, okay? And all those problems are about quadratic functions, of course, parabolas, right? Okay, so I'm going to start talking now, lecturing, but do y'all guys have any questions that you want to ask, okay, about anything? If you've got specific questions about the test and how your test was marked, see me about that separately, okay, right? So we don't have to discuss that in front of the whole class. But if you do have questions about that, you're welcome to ask me, okay? Sometimes I make mistakes scoring tests. Not that often, but sometimes. All right. All right, so we're going to go back to the notes. I've got some, these were not really the last set of notes that we were talking about, but I want to show you something here. And we're going to do, this is part of the activity that we're going to do after class, okay? Actually, this is on the activity, so I'm not going to talk about this one. This is a word problem that is going to involve quadratic functions. It's kind of similar to some of the other word problems we saw back in Chapter 2, but when we come up with an equation for solving this word problem, it's a geometric problem, so it's like problems you saw, again, in Chapter 2. But when we come up with an equation, or in this case, it's going to be a function that we're going to use to help us solve this problem, it's going to be a quadratic function, okay? So that's what separates it a little bit from the things that we were doing in Chapter 2. And then here's another kind of problem that we took up in Chapter 2, but again, we're going to adapt it a little bit to this chapter, or maybe I should say that backwards. We're going to exploit parabolas instead of lines to help us think about this problem. All right, so here we've got a table of data again. So we've been working with tables of data since the beginning of the class, right? Okay, and so this table shows the percentage. So these y values here are percentages. I don't have the percent mark there beside them, but all these y values are percentages. The percentages of adult women who are working, okay, starting with 1950, okay, so this is the input here, X, is elapsed years from 1950, so the first value in the table, I guess, is elapsed year 12, so that would correspond to 1962. So apparently in 1962, 38%, a little bit more than a third, right, of adult women were in the workforce, okay? But of course, that number has climbed, right, as more women have taken jobs that in 1962. So you see there's been a pretty steady increase at first, right, in that that percentage of women working. But notice, then there's an interesting change here. This is the year, I guess, what would that be? 2002, right? Okay, that's 50 years from 1950, so that's 2002. Notice that percentage hit a peak of about 60%, okay, and then after that, the percentage has declined a little bit, okay, and that's kind of an interesting sociological question. I don't think experts actually know why this has occurred, okay, although there's lots of speculation about why that percentage has dropped. But you know, you might think that percentage is going to continue to rise, okay, but instead, around the year 2000, right around the turn of the century, that percentage peaked, and then in recent years it's come down, not a lot, but come down a little bit, okay. So it's kind of hit a plateau there, right, and then just dropped a little tiny bit. So what we want to do is, like in Chapter 2, we want to fit a curve to this set of data so that we can make predictions about the future, right? Okay, because our data stops in, this would be 2016. So the last year for which I have data is 2016. So if we want to make some predictions, say about next year, 2020, or in the future, right, we need to fit a curve, right, to this data. But notice then a straight line is not going to be appropriate here, okay, because straight lines are always either increasing or decreasing, right, okay, but this data, the y values are first increasing and then they start decreasing a little bit, okay, so a straight line is not going to be an appropriate model for this set of data, okay. All right, so what I've actually done here now is made a scatter plot of this set of data, okay, and so I'll show that to you now. And I made this scatter plot not by hand, but I did it here in Desmos, okay? So there's the scatter plot. The points there are the scatter plot, okay, for the set of data. And let me raise that graph just a little bit so we can see that top point. And so what you can see there, right, is that as I mentioned, right, you can see this from the table as well, right? First, right, the y values are increasing, correct, okay? And then they reach a peak there, right? And again, this is in 2002, and then they start falling off again, right? So if you, again, if you try to fit that a set of data with a straight line, you can do that, okay? But that straight line really won't capture, right, sort of what's been happening in the data, right, that the data sort of peaked and then starts falling off, all right? But when you're looking at the scatter plot, notice that you see more of a curve, right, than a straight line, and a parabola might be an appropriate curve or a better curve to fit this set of data. So what I've done is I've used a parabola, right? Okay, remember a parabola, U-shaped curve, right, to fit the set of data rather than a straight line. Now, we could have tried to draw that parabola by hand that we think fits that set of data, but that's going to be a lot messier than trying to draw a straight line, okay, by hand, all right, to fit a set of data. So I've relied on the computer to fit this parabola to this set of data. So here's the parabola, the U-shaped curve, right, that the computer says is the best parabola to fit that set of data. Okay, and it's a parabola, so it's got a formula that corresponds to a quadratic function. All right, and in a minute we'll write down the formula for that quadratic function. But it's this now curve that we can use to make predictions, right, about what's going to happen here in the what's going to happen in the future, right? So if we were going to predict the percentage of, or to make intelligent predictions, maybe not perfect predictions about what's going to happen in the future, right? So if we were going to try to predict what's the percentage working next year in 2020, this is of adult women. Let's see, what X value would that correspond to, 2020? Doris, what X value would that correspond to? So we began with counting here in 1950, all right? So our inputs are elapsed years from 1950, Doris. So 2020 would be how many elapsed years from 1950? Just how far is 2020 from 1950? What's the difference between 2020 and 1950? 70, right, okay, so that would correspond to 70 there in our table, right, okay, and so there's 70, so we can go up and just look at the graph, right, and see what's the y value that corresponds to 70. We have to read that kind of roughly, but let's see, that's 50, and this is 60, so that must be, what, 52, 54, maybe about 55, okay, is right there. On the y-axis, so we might predict there about 55% looking at the curve, right? If we wanted to go out to 2030, that would correspond to 80, all right? That's kind of far out, 10 years from now, to use this data, but we could still make that prediction, right? So that would correspond to x equals 80, and that looks like it's right there, which is right at 50%, right? Okay, yeah. Okay, so so that's how we would use the curve, right? Okay, to make predictions. All right, now there we're just eyeballing things, but actually we're going to get a formula also for the curve. All right, so Desmos will provide us with that. So let's see if we can see that. All right, and it's over here on the left-hand side, okay? And Desmos levels things a little oddly, but you can still figure out what it's trying to tell you there, because there is sort of the formula, right? Okay, for a quadratic function. Remember, a quadratic function has that form ax squared. Desmos puts a subscript here, but you can sort of ignore that. So ax squared plus bx plus c, right? Okay, that's what quadratic functions formulas look like. And Desmos tells us what these three coefficients are. So the a value is this little tiny value minus 0.0122675. What's that a value called, by the way? It's got a name other than a. Okay, how do we refer to that? What, Arthur? Yeah, not the slope, okay? Yeah, quadratic functions don't have slopes, okay? Only straight lines have slopes, all right? So what? Leading coefficient, right? That's the leading coefficient. And then B doesn't really have a name, but I call that the middle coefficient. And then the C value here is the constant coefficient, which here is 22.2422, right, apparently, to 4 decimal places. Remember, that's going to correspond also to the y-intercept of the curve. I don't think that has any meaning to us in this particular context, but that is the y-intercept of that quadratic formula. All right, so let's write that down. Okay, so can y'all write those down for me, because I'm going to have to switch screens there. So write down those coefficients for me so I can copy them into the notes. Be sure you take the decimal places, okay? Because sometimes these fitting curves are really sensitive to decimal places. So if you drop some of the decimal places and then plot them, you get a much different curve, okay? Sometimes that happens. So even though it's a little bit clumsy to write down all of those, or cumbersome to write down all those decimal places, try to include them, okay, if you can. Especially when you're going about making predictions. All right, y'all get those? Someone get those? So, so what's my formula there then of my parabola that fits this data? What was the leading coefficient? It was minus something, right? 0.012. What else there? Say that again for me. Another 2. 675. Okay. So that's the leading coefficient, right? Remember, that's going to be multiplied by x squared. What was the middle coefficient there? 1.32977, right? Okay. And then that last coefficient was, I remember it started with 22. What were the decimal places there? 2422? Ah, okay. So there's the formula for that parabola, all right? So a little bit messy in the sense that it has these coefficients with all these decimal places in them, but it's still just a formula for a quadratic function, right? Leading coefficient, middle coefficient, and constant coefficient, right? So it's just got the same form. And now you can use that, right, to make predictions about, again, years in the future that you like, right? So if you wanted to predict, like we did using the screen, right, using the graph, if you wanted to predict the percentage working in 2020, right, okay, just take 70, okay, make sure you get the right elapsed year, right, and just copy that into your formula, okay, and do the calculations. So wherever in this formula, right, I have x to make a prediction about 2020, of course, I will just substitute there 20, all right? So we're going to have here 20 squared. Don't forget to square it. And then here, right, 20, okay, and then plus the 22.2422. What now? I'm sorry, 70. Thanks for catching that. So you have to do a little bit of a computation, right, with your calculator to make this prediction. But at this point, it's just arithmetic, right? Just calculator work. Now, this screen where you can fit a quadratic function to a set of data, if it's appropriate. So you want to see a scatter plot, right, that kind of has a parabola shape to it. That's when it might be appropriate to fit a quadratic function to a set of data. Remember that that parabola may open down, correct, like this one does. This one has leading coefficient negative, right? So that makes it open down. But if your scatter plot maybe look like this, okay, you can still fit a quadratic function to that, except when you fit that function, you'll get a positive leading coefficient, right? You'll get a parabola that's opening upward. But anyway, the screen where you can find that Desmos tool that is available in MyMathLab. Okay, so if you go to your home page, to the announcements. So your home page is going to look something like this, okay? And then in the announcements, right, there's the link to this tool, okay? So you can just click on that, and all you'll have there is a table that you need to fill in. So it looks very similar to the linear regression tool that we used, okay? Except this screen is going to fit a parabola instead of a straight line. This is just sample data, okay, just to demonstrate this. So you would just, to fill in your table of data, right, you would just type over these values, okay? Notice this parabola, right, for this set of data does indeed open up, right, okay? And because of that, if we look here at the leading coefficient, you're going to see that's going to be positive, right? Again, you get a really lots of decimal places there, a small leading coefficient, in this case 0.0822585, right? But that is positive, right? Because that parabola is opening upward. If we wanted to find that vertex there, how does one find the vertex of that parabola? So do you recall that that formula? What now? No pies, fortunately, okay? There's a formula for that, right? Okay, and so to find the x-coordinate of that vertex, okay, so that low point on the parabola. By the way, that's also where the parabola, in this case, shifts from decreasing to increasing, right? Okay, at that vertex. To find the x-coordinate of the vertex, which it looks like is pretty close to 7 here, but maybe not exactly 7. Okay. Remember, you take minus b over 2a. All right. So you take the negative of the middle coefficient. All right. Take the negative of the middle coefficient, and then divide it by twice the leading coefficient, and that gives you the x-coordinate of the vertex. How do you find the y-coordinate of the vertex? Which here looks like it's going to be kind of close to 1, right? But just a little bit below 1, maybe. So once you found the x-coordinate, You plug it into the formula, sure, right. Okay, that's a y value, right? So you can get the y value that matches the x coordinate of the vertex just by taking the vertex x value, right, and plugging that into your formula, okay? So the only thing you really need to remember is how to find the x coordinate of the vertex, and you do that by, again, taking minus b, so in this case that's negative a negative, so that's going to be positive, right? And divide it by twice the leading coefficient, okay? All right, so in our activity today, actually we're going to practice this a little bit because you have a homework problem that asks you to do this as well, okay, in the 3.1 homework. So on our sheet, we're going to model a set of data. Actually, this is a data set that came from the test review, all right, for test number 2. And in the test review, you used a straight line to fit that set of data, okay? But on this activity sheet, you're going to use a parabola instead of a straight line, okay, to fit that set of data. When we get there, we'll show why we are using a parabola instead of a straight line, okay, to fit that set of data. Okay, all right, so there's another application of quadratic functions. We saw several of them so far, okay? So here's another one. Quadratic functions are useful sometimes for fitting sets of data for which straight lines are not appropriate, okay? Not all sets of data, you know, look like straight lines, right? This one in particular. Okay. All right, let's go back now to where we were in the notes right before the test, okay? We were talking about another aspect of parabolas, and that is finding x-intercepts of parabolas. And to find x-intercepts of parabolas, you often need to know this famous formula, the quadratic formula, right? One of the most famous formulas in mathematics, and that is used to solve equations of this type, okay? So if you had an equation that fits this format, notice the key thing to look at there is the fact that the unknown is squared. If you have a formula, an equation that fits this format, that's called a quadratic equation, okay? And you can solve quadratic equations sometimes by factoring, remember, okay? But you can also solve them, if you cannot factor, you can also solve them by using this formula, all right? And so all you have to do is plug values into this formula. You just have to know the leading coefficient, the middle coefficient, and the constant coefficient. Plug them into this formula. Do a little bit of arithmetic simplification. Sometimes easier said than done, okay? But do a little bit of arithmetic simplification, and you will get the solutions to your equation. Sometimes, or often, in fact, two solutions, because you get two solutions here from this formula by either adding or subtracting this square root from the minus b value, okay, before you divide by 2a. All right, so you've practiced with the quadratic formula before, okay, because that's a very common formula in algebra. And we practiced with it also last time, okay, with this example, but so we're going to see another example here where we were asked to find the x-intercepts of this parabola. So if you graph that function, you're going to get a parabola, okay? Of course, it may have x-intercepts. It may cross the x-axis. It may also not cross the x-axis, right? Okay, but it may cross the x-axis. And so if it does, we wanted to find the x-intercepts. One way, and of course the way you find the x-intercepts for any function, whether it's a quadratic function or not, is you take your function formula, right, and you set it to 0, and then you have to solve that equation. So y'all did that on the test pretty well, okay, except it was a very easy function. It was just a linear function, and so you took the linear function and set it equal to 0, and you just solved that equation, okay, and it turned out to be a pretty easy equation to solve. But for quadratic functions, when you take a quadratic function formulas and set them to 0 and solve, you get much more challenging equations to solve, okay? So it's harder to find the x-intercepts for quadratic functions, and that's where the quadratic formula becomes helpful, all right? All right, so we saw an example of that in the notes last time, so I'm going to go back through that example. Let's just take another example here, okay, of quadratic function, and see if we can find its x-intercepts. Of course, we could also estimate the x-intercepts, so don't forget, you can also estimate the x-intercepts, right, by making a graph, all right, okay? So you can make a graph of this parabola, and when you graph that, you are going to get a parabola, right, okay? You can make a graph of that parabola and look at the graph and estimate the x-intercepts from the graph, okay? But that's only going to give you estimates, right? By solving this with pencil and paper analytically, we can perhaps find precise values for the x-intercepts, right, and not estimates. So let's try that. This function is called k. By the way, let's convince ourselves first that this question even makes sense. So I said find the x-intercepts of that parabola, but parabolas do not always have to have x-intercepts, right? So it could be that this is a bogus question, because it could be that this parabola does not have any x-intercepts. What's a picture of a parabola that doesn't have x-intercepts? So what would keep a parabola from having x-intercepts? Well, yeah, that's right. It doesn't touch if it touches the x-axis, right, it's going to have x-intercepts, Kevin. So how could we draw a parabola that doesn't touch the x-axis? So how can you miss the x-axis completely when you draw a parabola? Remember, parabola, U-shaped curve, right? So how can you draw a U-shaped curve that's going to miss the x-axis? Can you just position for me a parabola on there that would miss the x-axis? Well, just describe to me how to draw one. Okay, that's not quite enough description, all right? It would be a U that doesn't touch. Yeah, so how can you draw a U-shaped curve that's not going to touch the x-axis, Kevin? What now? Oh, the vertex above the x-axis. All right, so vertex above the x-axis, so let me just put it there, for example. That's above the x-axis. And what else, Joshua? See, you can have the vertex above the x-axis, and if the parabola opens this way, you're going to touch the x-axis. So you have to say a little bit more. Vertex above the x-axis and what? And the parabola is opening upwards, okay? When you say lines, you mean the left and right-hand side? Yeah, okay. All right, so those are not lines, right? Okay, but those are curves. But there you have it, right? Okay, so if you had a parabola position like this, correct, okay, a vertex above the x-axis, but the parabola is opening upward, okay? So that parabola is not going to have any x-intercepts. You can also do that by putting the vertex below the x-axis, right, and then having the parabola open downwards. That parabola also not going to have any x-intercepts. So just because I ask you to find the x-intercepts of a parabola doesn't mean that you're going to have any, all right? Okay, that may end up not having any. Yeah, Montel. Flip the U horizontally? You mean opening to the left or to the right? But just in general, so I could have like this. Not that far. A little lower. Okay, I don't think if it's opening to the left or the right, remember this U-shaped curve, there's any way to keep it from touching the x-axis. All right, there's no way to keep it from touching the x-axis because you can have it opening to the left or the right, by the way, okay? Well, in general, you can have parabolas that are opening to the left or the right, but there's something wrong with a parabola like this, All right, we'll talk about that in just a second. But even if you get it opening to the left or to the right, you're not going to be able to stop it from crossing the x-axis eventually. It may take a little while, but ultimately it's going to cross the x-axis. All right, this branch is going to keep going up to infinity. It may do it very slowly, but it's going to keep rising all the way to positive infinity. So eventually it will cross the x-axis. But there is something wrong with this curve, Montel. So even if you took this and rotated it to get took this curve and rotated to get this one, you would have a curve that is not a what? Yeah, this is not a what? What are we going to say there? It's not a function, right? Okay, that curve is not a function, all right, because you have inputs there, right, that have two different matching outputs. Okay, so we wouldn't be thinking of this type of curve, all right. It wouldn't be a quadratic function. Okay, it wouldn't be a quadratic function. Now, you may, in future math courses, actually study this type of curve, okay? They're still parabolas, but they're not functions, okay? May be perfectly useful, but they're not functions. All right, so, well, let's test this one then, okay? So let's see if this, before we try to find the x-intercepts, let's see if this one really does have any x-intercepts, right? Okay, so I'm going to erase your example, Montel. So let's see if this one really does have any x-intercepts, okay? And so I want to see if it's got one of these bad situations, right? The vertex is above the x-axis and the parabola opens upward, okay? That would be bad. Or the vertex is below the x-axis, right? And the parabola opens downward. All right, so which way does this parabola open? Well, you can tell that from looking at the coefficients, right? So what's the leading coefficient here? Minus 1/2, that's right, okay? So the leading coefficient is minus 1/2, which is negative, obviously, right? Minus 1/2 is less than 0. So which way is that parabola opening? Down, right, okay? So it's opening down. So it's not like this picture, right? It's opening down instead of up, all right? So we're hoping that the vertex will not be below the x-axis, because if the vertex is below the x-axis, right, we've run into issues, correct? All right, so, so how do I find the vertex? Oh, I think we just talked about that, right? Okay, so how do we find the vertex there? Oh, by the way, let's write down the other coefficients because we're going to use them here. What's the middle coefficient? -1. Yeah, don't write 1. It's -1. And what's the constant coefficient here? 2. Oh, that already gives me a clue here, right? Okay, that helps me already. It crosses the y-axis at 2. Ah, okay. And so it crosses the y-axis right there. But which way does it open? Down. So I'm thinking it's going to hit the x-axis, right? Okay, it's got to hit the x-axis. It crosses this point, and it's opening down. So I think already I can tell it's got to cross the x-axis. Oh, that was lucky. But let's go ahead and find the vertex anyway, because we can completely settle the question by figuring out what the vertex is. All right, and we need to remind ourselves of that vertex formula anyway. So let's see. The x-coordinate of the vertex is going to be minus b. So that's minus a -1. All right, minus a -1. This minus is part of the b, right? But then in the formula, you have a negative. All over what? 2 times the leading coefficient, right? Which is here what? -1/2, right? Okay. So how does that simplify? That comes out kind of nice, right? That's what? 1 over -1, right? Okay. 1 over -1, which is -1. Okay. So the x-coordinate of the vertex is at somewhere here at -1. Right there, okay, approximately, right? I'm drawing this very roughly, okay? So right here is the x-coordinate of the vertex. And then how do we find the y-coordinate? What do you do with the -1? Plug it in, right. So you plug it into, this function is named k. So I'm going to calculate k of minus 1. Let's see what we get here. So I have minus 1/2 times minus 1 squared minus a minus 1 plus 2. And now let's do a little bit of arithmetic here. So minus 1/2 times 1 plus 1 plus 2. What does that turn out to be there? 2.5, exactly, okay, or 5/2 if you want to. So there is your vertex, is at minus 1 and 2.5, which is above, right, okay, the x-axis. Maybe right about there. I think I drew it a little bit too high, but that's okay, right? And this thing is opening downward. Remember, it hits the y-axis at 2, so it's going down there and crossing 2 at the y-axis and then coming down over here also. So it definitely does cross twice the x-axis. So we have 2 x-intercepts there that we can find. Oh, that's great, okay? So at least we know the problem makes sense, right? There are a couple of x-intercepts for us to find. So I think we mentioned this before, but let's remind ourselves, how many x-intercepts can a parabola have? It may have none, so it can have 0, right? That corresponds to this picture, right? It could have 2, because this function k is going to have 2. What's the other possibility? 1, right, if the vertex exactly is on the x-axis, all right? So it is possible for the vertex to be right on the x-axis, and then it's going to have 1 x-intercept, right? But it can't have more than 2, all right? Never going to have more than 2, right? Just no way to make that curve, right? That U-shaped curve cross the x-axis more than 2 times. So 2 is the most you're going to get. All right, so now let's find those, okay? So remember, you find the x-intercepts, right, by, like it is for any function, take the formula and set it to 0, and then you just have an equation to solve. And that's often easier said than done. Sometimes equations, not easy to solve, right, okay? But here, since this is a quadratic equation, the unknown is squared, the x is squared, right? This means that we have a couple of techniques. We can try factoring, but I don't think we're going to get very far with factoring. That minus 1/2 is going to make that expression on the left difficult to factor. So if you're not able to factor, you don't quit, right? You can use the quadratic formula. So let's see what the quadratic formula says. All right, so do you remember that formula now? It's minus b plus or minus square root of b squared minus 4ac all over 2a. That's one that you really should commit to memory, okay? Even if you can write it on the survival card, you should really memorize that one, because that one just occurs so frequently. All right, so let's start plugging in these values. So let's see. Remember, a was minus 1/2, right? B was minus 1, and C is 2. So we get minus a minus 1 again, right? Plus or minus. Be careful about the signs. And then minus 1 squared. Minus 4 times A is minus 1/2, and C is positive 2. All over 2 times minus 1/2. You got to be very careful about the signs, because a sign mistake will lead to disaster, right? So if I make a sign mistake, be sure to stop me here, because otherwise we'll have to retrace all of our work and fix it. So let's see. This is 1 plus or minus. The square root of minus 1 squared is 1. And now let's see what we're going to get for that second term under the radical, okay? And this is the one where if you're going to make a mistake, this is where students often make the mistake. So let's see. Minus 4 times minus 1/2 is positive something, right? Positive what? 2. But you have a now times another 2. So this second term ends up being positive 2, okay? Oh, no, I'm sorry, positive 4, right? So nice. So plus 4, and then the bottom is going to be minus 1, correct? So we have 1 plus or minus the square root of 5. Not much we can do with the square root of 5. 5 is not a perfect square, and you can't even simplify it. And then all of this divided by minus 1. Well, I really don't have to write the minus 1 in the denominator, right? Okay. It is negative, though, so that means the signs are going to change here. You can divide by minus 1 by changing the signs in the numerator. So this plus becomes a minus, and then these two signs are going to switch. So the positive will become a minus, but the minus will become a plus. So you still end up with a plus and a minus there. So we get minus 1 minus plus square root of 5. Okay? There are your exact values for your two x-intercepts. One of them is minus 1 minus the square root of 5, and then the other one is minus 1 plus the square root of 5. Okay. Let's see. Approximately now, what are these numbers? Because these are the exact values for the x-intercepts, but if you wanted to say plot those x-intercepts or use those x-intercepts for some other purpose, you probably want to know what these numbers are, right? Okay, so you need your calculator to give you an estimate. Let's try to a couple of decimal places here. What's minus 1 minus the square root of 5? Negative 3.24. Yeah, I think that's right. Minus 3.24. And then this one is 1.24. Okay. There you go. So in our very ugly graph here, right, this x-intercept, that ugly graph was actually surprisingly accurate, wasn't it? This is minus 3.24, and this is 1.24, right? Okay. There are your two x-intercepts. It's minus 3.24. I really messed that up. Minus 3.24 right there, okay, for the first x-intercept. That really crude graph, I think, turned out to be sort of fairly accurate, and that reminds me of something that's important. That's going to be important for test number 3. You are going to need to be able to graph parabolas by hand, okay? So just like with straight lines, parabolas are not that difficult to graph by hand, okay? So we'll want to be able to graph those by hand. You don't get many opportunities for doing that, however, in your homework, right? Because you're not doing things by hand on the homework. So on the test review, for instance, you will have some examples of graphing parabolas by hand. And so it's really important to do the test review for test number 3, so you practice that a little bit before you take the test. Again, not difficult to graph parabolas by hand, okay? You can get really accurate graphs even by hand of parabolas. All right, so let's see. There's our second example there of using the quadratic formula. All right, okay. Let's see if we can figure this one out. So this problem kind of goes back to more like the beginning of the course. So it seems like we're redoing something that we've already done, but we're not redoing it, we're just revisiting it, all right? So we want to find the domain of this kind of messy function here. That's kind of a messy function, right? So we don't want to graph it. This one would be hard to graph by hand, so we would really rely on the computer to help us make a graph. But I think one thing we can do here, I think, is try to figure out what is the domain, okay, of this function, okay. So how do we do that now? So we got to just remind ourselves, how do we find the domain of a function like this? What's the issue in this problem? So often the domain for functions is all real numbers, but the domain for this function, I think, is not going to be all real numbers. So what's the issue here in the formula that's going to keep the domain from being all real numbers? The denominator, right, Arthur? So if you have a formula, right, that involves a function formula that involves a denominator, and you want to find the domain of that function, what did we do? Recall what did we do back on test 1? Leslie, what did we do back on test 1 to figure that out? Set what equal to 0? Denominator, right, because remember, you cannot divide by 0, correct? So you take your denominator and set it to 0, and then you have to solve that, and then throw those solutions out of the domain, right? You don't want those solutions in the domain. So we're going to do exactly the same procedure, okay? It's just going to turn out to be a little bit more complicated here. So we're going to take that denominator, which is 3x squared minus 6x minus 2, and set that to 0, and then solve that equation, and then whatever solutions we get, if we get any solutions, we may not get any solutions, but any solutions we get to that equation, we're going to toss those out of the domain. So, so when we set that denominator to 0, what sort of equation do we get there? Quadratic, right? That's called quadratic, okay? So really important to remember the terminology. You're not just going to hear me say it, but in your next math class, the professor's also going to say it, and they're not going to stop and remind you what that means, okay? So this is a quadratic equation, okay? And so we can try factoring to solve that quadratic equation, but we always have the quadratic formula available to us. So just to practice the formula, let's use the quadratic formula here. Even if we could solve this by factoring, let's practice the formula. There's going to be a problem or problems like this in the homework, and you're going to find these hard, okay? I know because the homework problem, I think, that's like this type of problem has a video on it. And I know how many times the video has been watched. And that video is the most watched, or one of the 2 or 3 most watched of the homework videos. Okay, so I know that this is the one of the harder homework problems. All right. Okay, so, but here's how it works. You take the denominator and set it to 0. Okay, and now let's try to solve this quadratic equation using the quadratic formula. So I need to identify my coefficients. What's my leading coefficient here? 3, right? And my negative 6, and the c is minus 2. If you don't have by the way, if you have a quadratic equation and it's not simplified and set to 0, be sure you simplify it and set it to 0 first, but before you try to use the quadratic formula, because you've got to have it simplified and set to 0 before you can identify the 3 coefficients. All right, well, anyway, we know what these coefficients are, so let's plug them in. So I know that x is going to be minus a minus 6, plus or minus, because I may get 2 solutions to the equation, and then minus 6 squared, that's b squared, right? Minus 4 times a is 3, and c is negative 2. All of this over 6, right? 2 times 3. So I get 6, positive 6, plus or minus, square root of 36. And now let's be careful here. So minus 4 times 3 is negative 12. But negative 12 times minus 2 is positive 24. Positive 24. So you're going to write down here plus 24 over 6. That's good, okay? I now know that I am going to get 2 solutions to this equation, okay? Actually, there they are, all right? But we're going to simplify this a little bit by hand. But there are the 2 solutions. One of them is 6 plus the square root of 60 divided by 6, whatever that number is. And the other one is 6 minus the square root of 60 divided by 6, okay? So there are the 2 solutions quadratic equation, okay? But again, I'm going to simplify this a little bit by hand before I stop. Forgot what I was going to say. Oh yeah, if the quantity under the radical, if for some reason this quantity under the square root turns out to be negative, that means you don't have any solutions. Well, let's caution ourselves there. No real number solutions. No real number solutions. But fortunately, this is plus 60, right? And so we are going to have two real number solutions there. All right, let's try to simplify those a little bit more. So I have 6 plus or minus the square root of 60 over 6. And you can't completely simplify this because 60 is not a perfect square. But what I'm going to do is try to write 60 as a perfect square times something else. So can you write 60 as a perfect square times something? There's lots of ways of writing the number 60 as a product. By the way, this is why there are 60 minutes in an hour and 60 seconds in a minute, because the number 60 has lots of factors. So how can you write 60 as a product where one of the numbers is a perfect square? 6 times 10 won't do it, okay, because neither 6 nor 10 is perfect square. 2 times 30 won't do it, right? 4 times 15, there it is, okay. So 60 we can write as 4 times 15, and the reason I like that is because I can extract square root of 4. I cannot extract the square root of 15, but I can extract the square root of 4. That gives me 2. So I end up with 6 plus or minus 2 square roots of 16, 2 square roots of 15 over 6. Now, from the top, the 6 and the 2, I'm going to factor out a 2. So I would have 2 times 3 plus or minus the square root of 15, again over 6. And the reason I factored the 2 out is because 2 goes into 6 3 times. So there's where we have to stop. That's it. I cannot, by hand, without using a calculator to get an estimate for square root of 15, I cannot simplify that by hand any further. So there are the two solutions to your equation. There are the two numbers you cannot have in the domain of this function. So the domain of this function is all real numbers except these two, okay? 3 plus the square root of 15 divided by 3, and the other one is 3 minus the square root of 15 divided by 3. So see, you're familiar with this process, right? It's just takes a little bit more work, right? To find the numbers that you want to exclude from the domain. Okay. I'm going to come back to this example. We don't need this one immediately, so I'm going to come back to that one next time. And because I want to just briefly introduce what's coming up, okay? All right, so one of the things I just mentioned, we didn't see it, but one of the things I just mentioned in the previous example is we cannot extract square root of a negative number, okay? So far in our mathematical knowledge, square roots of negative numbers don't exist, okay, right? But in mathematics, that's not quite the case, all right? It turns out that it actually is useful to define square roots of negative numbers. So that's what we're about to do here, okay? But it is the case that the square roots of negative numbers are not part of the real number line, okay? So square roots of negative numbers not going to be real numbers, right? So they're not going to exist on the x-axis, for instance, which is a real number line. Now, here's a real number line, right? Okay, it looks like the x-axis, correct? So all the numbers that probably that you've encountered for most of you in your life so far have occupied positions on the real number line. Okay, they've been part of this big, gigantic set of numbers. And there are lots of subsets of the real numbers, important subsets. One of them, one important subset of the real numbers are called the rational numbers. So these are numbers that can be written as fractions. So any number that can be written as a fraction, that's called a rational number. So that would include numbers like 22/7 or decimal numbers, right? Because decimal numbers can be written as fractions. And also repeating decimals can be written as fractions. So, of course, you're familiar with fractions. Now, some numbers, however, cannot be written as fractions. No matter how hard we try, you cannot write the number down as a fraction. Those are called irrational numbers. Square root of 2 is a famous example of an irrational number. You cannot express that number as a fraction, but it's still a real number, okay? It's part of the real number line. It occupies a position on the real number line. Pi is another famous number, Montel, you mentioned earlier, okay? That's an irrational number. You cannot write pi as a fraction, but it does still occupy a position on the real number line, okay? Another famous irrational number that we're going to visit later in the course a little bit is this number designated by the letter E. Okay, this is approximately, but not exactly, 2.718. It actually has a non-terminating, non-repeating decimal expansion, though. The first three decimals are 718. Okay, and that is another famous irrational number. You cannot write this value E as a fraction, okay? But still, it occupies a position on the real number line. Of course, when you were younger, right, you dealt with simpler types of real numbers other than irrational or rational numbers. When you were in first grade, right, you worked with natural numbers, like 1, 2, 3. Those are the counting numbers, numbers you count with. And then when you grew up a little bit, you learned about the 0 and then also the negatives of the natural numbers, like -10 or -3 or -4. Those numbers are called integers, but also part of the real number system. So these numbers have all the properties that you've come to expect of real numbers, right? You know how to do arithmetic with them, add, subtract, multiply, and divide them, right? Okay. You know how to count with them, of course, right? Okay. That was the first thing you probably learned to do with numbers, is count, all right? While you were watching Sesame Street, okay? So this set is well known to you, right? It's still kind of mysterious. It has lots of mysterious properties that you're probably not aware of, but a lot of it, but still you're really familiar with this set of numbers. All right, okay. But now we're going to introduce a totally new set of numbers, okay? And the way I'm going to do that is by defining square root of -1, okay? So up until, again, this point in your life, you may have just simply dismissed this value as not meaningful, okay? But it actually is meaningful. It has important applications. It's just not part of the real number line, okay? All right, I'm going to demonstrate for you now that square root of -1 is not a real number, all right? If you needed proof of that, okay? Probably you would accept that, right? Okay, but I'm going to demonstrate to you that it's not a real number. All right, this is easy to do, okay? Because what I'm going to do is take the square root of -1, okay, and then I'm going to square that, okay? So I'm going to take square root of -1, and I'm going to square it. Of course, what does it mean to square something? Multiply it by itself. So what I'm doing here is I'm going to multiply the square root of -1 times the square root of -1. Now look, if this number really is, that I'm claiming is the square root of minus 1, if it really is the square root of minus 1, when I square it, what do I have to end up with? How do square roots work anyway? If you take the square root of 2 and square it, what do you got to end up with? What makes something the square root of 2? Do I need a simpler example? Suppose I take the square root of 4 and square that. Okay. Well, what is the square root of 4? 2. And of course, 2 squared is what? 4, right, yeah. When you take the square root of 4 and square it, what do you have to end up with? The same number, correct. So if I take the square root of 2 and square it, I have to end up with what? 2, right, okay? Yeah, right, there's no way around that, right? Or if I take the square root of 3 and square that, I'm supposed to end up with 3, correct? Well, the same logic applies here. If you take the square root of minus 1 and square it, you have to end up with what? Negative 1, right, okay? You've got to end up with minus 1, okay? You must end up with minus 1. All right, so, but think about how real numbers work. If square root of minus 1 is a real number, right? If it's a real number, that means it's got to occupy a position over here on the real number line, correct? So there's only 3 places it could be. One is right here to the left of 0. If it's to the left of 0, what's its sign? Negative, right, okay? So you would have a negative value times a negative value, and when you multiply a negative real number times a negative real number, what happens? Yeah, it comes out positive, correct, okay? But it has to turn out to be minus 1, right? So we know that square root of minus 1 cannot be here, right? Cannot be to the left of 0. Well, it could also be maybe here. It could be to the right of 0. If it's to the right of 0, what's its sign? So if this were a real number, you would be taking plus times plus, and when you multiply 2 positive real numbers, you get positive. But can't have that, right? Because square root of minus 1 times square root of minus 1 has to be negative 1. So this possibility is gone. That possibility is gone. There's a third possibility, though, okay? Where's the other last place it can be located if it were a real number? It could go right there, okay? Because 0 is not positive and 0 is not negative. 0 does not have a sign. But if this is 0, if square root of minus 1 is 0, you have 0 times 0, but what does that equal? Which is not minus 1. So it ain't here either, okay? Those are the only 3 spots that real numbers can be, right? They've either got to be to the left of 0, to the right of 0, or 0, okay? Right in the middle. So square root of minus 1 does not occupy a place on the real number line. It's not a real number, okay? Not a real number. That does not mean, however, it is not a number, all right? It's not part of the real number system, but this is a number, okay? And it's going to be useful to us in a myriad of ways, okay? So, so what we don't want to suppose here is the square root of minus 1 is nothing. It doesn't exist, all right? That's what we do not want to say, okay? It's not part of the real numbers. That's a very familiar system of numbers to us, right? Okay, but that doesn't mean that it doesn't exist, all right? Not every useful number has to be part of the real number line, okay? There are other important sets of numbers outside of the real number line, and this is one of them, square root of minus 1, okay? All right, so we're going to make use of that value. All right, now, we have to learn about how square root of minus 1 works, right? It is a number. What sort of things do you do with numbers? Sometimes you count with them, okay? Yeah. What else do you do with them? Add them? Subtract? Divide, right, okay? So, that's arithmetic, okay? So, that's one thing I'd like to figure out. How do I do arithmetic with this weird number, okay? Square root of minus 1. Well, all right, we're going to learn that, okay? All right, let's stop there then, okay? And, yeah, we'll take a slight break, and then we're going to come back and work on our activity sheet. Did you pass that out, Taylor? Okay. Yeah, so we're going to work on our activity sheet, the first couple of problems on the activity sheet. You will need to be able, on the second one, to access your MyMathLab. So if you need a iPad, we'll get one for you, okay?